Hi again, and welcome to Lesson 6 of Artificial Intelligence and Machine Learning Foundations course. For today's lesson, we'll talk about data analysis in Python. This topic highlights the use of Pandas library. We'll explore commonly used functions in Pandas for data manipulation, analysis, and visualization. Pandas is an open-source Python library that offers high-performance and easy-to-use data structures and data analysis tools. The name Pandas is actually derived from the word panel data. And you must know that Pandas is built on top of NumPy, so we'll be dealing with somewhat similar data structures under the hood. And if you're not yet familiar on how NumPy array works, I recommend watching Lesson 5 of this course first. The two primary data structures in Pandas are Series and DataFrame. A data frame is a two-dimensional data structure composed of rows and columns, pretty much like a simple spreadsheet or a database table. Each column of a data frame is called a series. These columns must be of the same length, but they can be of different data types. Like a database table, data frames' size and values can be changed. This allows operations to alter values or add and delete columns to and from a data frame. To understand this further, I'll start with the Pandas series. First, I need to import the three libraries that we are going to use: NumPy, Pandas, and Matplotlib. Since Pandas series is simply a one-dimensional labeled array, you create a series similar to creating a list or a one-dimensional NumPy array, or any array-like object. In this case, I'll generate 5 random integers from 0 to 100, using the NumPy random.runIn function. Then, I'll call the Pandas series function and pass in this array of random integers. This creates a Pandas series. Now, you'll see two lists of numbers being displayed. The one on the right are the series data, represented by 5 random numbers, while the one on the left is an auto-generated index, quite similar to a NumPy array index. In Pandas, we also refer to this row index as the axis label. So what's the difference then? By default, a zero-based numeric index is automatically assigned by the series function if we don't explicitly specify the index upon series creation. This means we can assign any non-numeric index values to our Pandas series upon creation if we want to. Say I want to give an index of type string for each data in this Pandas series. I'll pass in another argument in this series function, index. In a Pandas series, index could also be any array-like object so long as it is hashable and has the same length as the data. Note that non-unique index values are also allowed. So don't be confused by this. It is a feature and not a bug. So you might notice that this resembles to a Python dictionary. And in fact, you can create a Pandas series from a Python dictionary. When you pass in a dictionary in a series function, the dictionary key acts as the index and the dictionary value acts as the data in the series. You can also create a series from a scalar value. For example, I can pass in a scalar value of 100. Now, when you do this, depending on how many indices you pass in, each will have a corresponding data of 100. Now, let's create a data frame. As I have mentioned earlier, a data frame is a two-dimensional data structure composed of rows and columns, similar to a spreadsheet or a database table. To create a Pandas data frame, you can call the DataFrame function and pass in a Python dictionary, list, series, or a two-dimensional NumPy array. For example, to create a data frame using a dictionary of series, first, I'll create 2 Python dictionaries, savings, and then expenses, and then I'll create another dictionary of series using the first 2 Python dictionaries of savings and expenses. Now, I'll pass in this to the DataFrame function to create a data frame consisting of 2 columns, one for each series. And as you can see, the keys in the series dictionary serve as the column labels of the data frame. And the key for each value in a Python dictionary serves as the data frame's row index, or often referred to as a row label. We can also create a data frame function from a Python dictionary of list. I can then pass in this Python dictionary of list to this data frame function together with the list of row index. The resulting data frame is the same as the first approach, using dictionary of series. We can also create a data frame from a two-dimensional NumPy array. Say, I have a NumPy array consisting of 5 rows and 2 columns. Now, when I call the data frame function, I'll pass in 3 arguments: the data, the list of row index, and the list of column labels. And the resulting data frame is the same as the first 2 approaches. For readability purposes, you may want to explicitly put the parameter name like index and columns, and it works the same. The index attribute gives us the row index or row labels, and the columns attribute gives us the column labels. Oftentimes, you will be working with thousands and millions of data items that are exported from a database or a data warehouse. Usually, these data come in a form of a CSV file or comma-separated values. So, to create a data frame from a CSV file, you can use the Pandas read CSV function. And simply pass in the file name as a string argument. When viewing large dataset, only few rows are displayed in your Jupyter Notebook. Here, we have a data frame consisting of 10,127 rows by 15 columns. By the way, this dataset comes from Kaggle.com. It is an online community of data scientists and machine learning practitioners where you can use over 50,000 public datasets. So, this dataset is about credit card-related information of few thousand customers. We can use it to practice how to use Pandas to do simple data analysis, understand the data that make a customer to churn or not churn, and eventually use machine learning algorithms to find patterns and build models from it. So, in here, we only see the first 5 rows and the last 5 rows of data. We can also do this by calling the head function, and it returns only the first 5 rows of data by default. We can pass in an argument to this head function to specify how many records we want to return. Say, just the first 10 rows. And if you want to view the last rows, you can use the tail function instead. We can also get the data frame information using the info function. Here, we can clearly see all the column names, the number of data items, 10,127, for each column, and its data type. Note that the string data type in Pandas is represented as object, same as an immutable string in Python. Usually, before you do any data processing and data analysis, you must know that data preparation is a very important step for you to have an efficient data analysis. This limits error and inaccuracies that can occur during data processing. Data cleaning is the first step to the overall data preparation. It is a process of analyzing, identifying, and correcting messy raw data. It involves filling in missing values, identifying and fixing errors, and determining if all the information is in the right rows and columns. So, the amount of time needed for data preparation for a particular analysis problem is directly dependent on the health status of your data. This lesson will not cover those topics, but just to give you some idea, for example, To check the summary of missing or null values in each column in your data frame, you can call the isNull function, which returns a Boolean value of true if null and false if it is not null. And then, apply the sum function to return the total null value for each column. And as you can see, everything here is 0, which is actually very good because it means there is no null value for all the variables that we are supposed to investigate. But if there are, then we have to decide with our business partner and agree on what to do with the missing data. When manipulating large dataset for data analysis, you would normally want to select subsets of your data from a Pandas data frame. For example, to get only the column customer age, you can use a dictionary-like syntax by enclosing the column name in a square bracket, like a key in a dictionary. This results to a Pandas series. You can get the same subset using the class-like syntax by using the dot operator. Since the resulting subset is a series, it has a row index associated with each series data. And if you want to get only the values as a bare NumPy array, you can access the values attribute. This gives us 10,127 numbers stored in a one-dimension NumPy array. There are times that you might want to get the count of how many times each number appears. Here, we can call the value counts function for the column customer age, and it gives us a total count for each age. So, we have 500 customers with the age of 44, and 495 customers with the age of 49, and so on. At the bottom part, you'll see that only one customer with the age of 70 and 73. It is worth knowing that Pandas is also good for data visualization. And when doing data analysis, you'll often need to visualize your data in different ways, so it can be presented and understood easily. For example, when performing a univariate analysis, histogram is a great way to show results of continuous data, like this customer age variable. You can call the hist function as an extension method of a class-like syntax like this, or a dictionary-like syntax, or you can call the hist function directly from the data frame and pass in the column name as an argument. Either way, the resulting histogram is the same. Since histogram is an approximate representation of the distribution of numerical data, you can also specify the number of bins, which is by default set to 10. Say I'll increase it to 20 to see smaller details of the distribution. In here, we see that the majority of the customers fall under the mid-40s. If you want to customize the X and Y labels of this histogram to make it more readable, you can use the matplotlib's pyplot object to do this. So, I'll set the Y label as the frequency, and then the X label as the customer age. And that's it. Another function that is very useful when you want to generate descriptive statistics that summarizes the central tendency, dispersion, and the shape of datasets distribution is the describe function. In here, you can easily see the count of 10,127 customer age. The average age is 46, with standard deviation of 8, and the youngest is 26, and the oldest is 73. It also includes the 25th, 50th, which is the median, and the 75th percentiles. Of course, you can get this descriptive data individually, like you can get the count by calling the count function, the mean, the median, and so on. To get only selected records from your data frame, we can apply fancy indexing using a Boolean expression. For example, if we want all the rows and columns of the data frame, where gender is equal to male, I can do this. This gives us 4,769 records. Or I can use the query function to filter data similar to a where clause in SQL. Say, I only want to use all the customers with marital status of single. Now, when we do this query function expects a string expression here. And since the marital status is of type string object as well, make sure to enclose it in double quotes as well. This gives us 3,943 rows. We can also include logical operators here, like filter it further to only single male customers, and this gives us only 1,818 rows. And then, from this data frame, say I want to investigate on the educational level of these 1,818 single male customers. I'll store the result of this query to a new data frame, df2, and get only the educational level column, and then let's describe it. So, we have 7 different unique values. The top educational value is graduate with a frequency of 550. Since the educational level is a categorical variable, we can use the Pandas group by function to group or split data according to its category and apply aggregate functions to the categories. So, I'll pass in the column that I want to group and then count each category. Now, we can clearly see how many single male customers fall under each category. And if you want to visualize this data, simply call the plot function and specify what chart to use. Say, I want a pie chart. I can customize the title of this chart that says, Educational Levels of Single Male Customers. You can always change the chart type. Say, instead of pie, I'll use bar. And I'll set the Y label to frequency. Also, you can change the rotation of the x-axis tick if it is hard to read by setting the rot argument and specifying the degree. So let's take a look at the original data frame again. And what I really want to investigate here is this attrition flag. This variable tells us how many customers have churned with a value of 1 and did not churn with a value of 0. So I'll create a variable called target and then set it to the column attrition flag and then group the data frame based on this target variable and get the count. And we have 8,500 customers who did not churn and 1,627 who churned. So let's plot this using the bar graph. And so far, it looks good. Now, let's try how to work with 2 variables. I'll create another variable called feature and assign the total trans count column to it. Let's view the data frame. Now, if I want to get a descriptive statistics of the total transaction count per group of customers, categorized as either churned or not churned, again, I can use the group by function. Apply it to our target variable, the attrition flag, and then describe the feature that we're looking for, which is the total transaction count. So in this table, we can see the 8,500 customers who did not churn has a mean total transaction count of 68.7, and the 1,627 customers who churned has a mean total transaction count of 44.9. Of course, we can see it easily in a bar graph. I'll copy this code and call the min function and plot using bar. I'll set the title, the Y label, then the X label. And it looks good. We can clearly see at a glance that the average total transaction count of churning customers is about 35% lower than the non-churning customers. When performing bivariate analysis, you are actually studying the relationship between two variables for the purpose of determining the empirical relationship between them. We call this correlation. A simple linear regression correlation is used when we want to measure two continuous variables. For example, say that I want to know the relationship between the total transaction amount and the total transaction count. Again, I'll create a list named features and then assign these two variables. I'll view the head of the data frame. And now, to know the relationship between these two variables, I'll call the core function. So, if this is your first time to encounter this kind of statistics, don't be intimidated. This value that you see is a correlation coefficient, which is a numerical measure of some type of correlation, meaning a statistical relationship between two variables. Understanding this value is very important. This value could range from -1 to +1. If this value is close to -1, it means that the two variables are strongly correlated, but in a negative direction. This simply means as the value of the first variable goes up, the value of the second variable goes down. However, if this value is closer to +1, it means that the two variables have positive correlation. Like in this case, 0.81. It denotes that as the customer's total transaction count increases, the total transaction amount also increases, which actually makes sense. Now, the value of 1 denotes a perfect positive correlation. Of course, because any variable is perfectly correlated to itself. So, when you want to visualize two continuous variables to instantly see if there is a correlation that exists, you can use the Pandas scatterplot. This function expects two arguments, x and y variables. So, I'll pass in features index 1 as x. This is the total transaction count. And then features index 0. This is the total transaction amount. And as you can see, this scatter plot instantly gives us the pattern of our data as a whole. As the customer's total transaction count increases, the total transaction amount also increases. So far, you have seen several ways on how you can select and filter subsets from a Pandas data frame. Now, I'll show you how to make selections that are more direct using either by labels or by integer locations, the loc and the iloc functions. You use the loc function when you want to select data from Pandas through its label, or you use iloc when you want to select data from Pandas via integer location. For you to understand this better, I'll create another data frame out of this and set a new index. Instead of using the default index of 0 to 10,126, I'll use the client num column. So now, for example, using the loc function, I can select rows starting from this row label up to this row label. Take note that in here, you use square brackets instead of parentheses. This creates a new data frame consisting of only 3 columns. And to return the same data frame using the iloc function, you specify the integer location instead of label. Here, starting from integer location 2, this is 0 based, up to integer location 4, exclusive of 5. So the resulting data frame is the same. Notice also that the loc function is inclusive of the range, while the iloc function is exclusive. Now, if you want to slice selected columns as well, simply put a comma and specify the columns. So now, for example, we can select a subset of this data frame consisting of only the attrition flag, total transaction amount, and total transaction count. I'll use the loc function. The resulting data frame only consists of 3 rows by 3 columns. I can accomplish the same result by using the iloc function. So, the integer location of attrition flag is 1, total transaction amount is at location 13, and total transaction count is at location 14. Also, same with the NumPy array. If you want full slices of either the row or the column, simply put a colon to it. It denotes all. So, as you have seen, Pandas is a very complex yet powerful tool that you will be using for your data analysis task. These are just some of the basic things that you can do with this package. And if you want to learn more, please refer to the pandas.pydata.org for the official Pandas documentation and tutorials. Up next, we'll build our first machine learning model using the scikit-learn machine learning library. And again, thanks for watching. And if you learned something of value here, please click the like and subscribe button for more programming tutorials. This is Joe Edgo, and hope to see you again in the next lesson.